Hello again, Physics 30s. In today's lesson, we are going to talk about Physics 30s. In today's lesson, we are going to talk about three different spectra of light. That includes the continuous spectra, the bright line or emission spectra, and the dark line or absorption spectra. Learning outcomes are to 1, describe that each element has a unique line spectrum, and 2, explain qualitatively the characteristics of and the conditions necessary to produce continuous line emission and line absorption spectra. I just wanted to point out that, again, before we made this transition from classical physics into modern physics, again, most of our physicists were pretty confident that they could explain most phenomenon, but like some of the major exceptions were the black body radiation curve, the photoelectric effect in terms of why is it that if you increase the intensity of light, you can increase the photocurrent, but not the speed of your electrons. And the other one that they were not able to explain is why each element has a unique line spectrum. And we'll get into that in a little bit today, although we're not going to quite provide an explanation yet because we're going to have to do a major rehaul of our model of the atom to do this. But what is a light spectra? A light spectra is a colored pattern that is produced when you either take light and you shine it through a glass prism. And when you shine light through a glass prism, the light undergoes dispersion. Dispersion just involves a separation of the light into its different color components. And the reason it does separate is because the index of refraction in glass does depend a little bit on the wavelength of the light that's passing through it. And those small variations in the index of refraction is what allows the light to separate into its color components. You can also get a light spectra if you shine it through a diffraction grating. So the diffraction grating is also capable of separating the light, and that's strictly due to the different wavelengths of light. And I believe when we looked at the equation for diffraction grating, it was the higher wavelengths of light you tend to locate them further from the central antinode in comparison to the lower wavelengths of light. So we're going to look at three different spectra. We're going to look at the continuous spectrum, the bright line spectra, and the absorption spectrum. The continuous one is nothing new. The bright line and the absorption one are going to be something a little bit different. Continuous spectra. Well, first of all, we're going to talk about how we produce white light. So there's a couple of ways you can do this. You can take a solid and you can subject it to a really, really high temperature. And if you get the temperature of the solid high enough, it'll start to emit white light. So that's one thing you could do. You could also take a very dense liquid and subject it to really intense pressure and temperature. And at that point, the liquid could actually emit white light as well. And what we're going to do is we're going to take that white light and we're just going to shine it through. In this case right here, we'll use a glass prism. So we take that white light, shine it through a glass prism. And again, I can just illustrate like where this is going here. So maybe we'll just take a black line. So here's our light source. There's a single slit right here. We're not trying to do diffraction. The point of the slit here is just to refine the beam. So just kind of like going in like one line. And then we have the white light is going to hit this prism. And then what we know, according to the dispersion of light, is that the violet light is going to be the one that refracts the most. So this could be violet, and then violet would go all the way up here. So what we'd see is at the very edge of this, we'd have violet light. That's the color that refracts the most. And then we also know that if you take white light and if you shine it through a prism, the red light bends the least. So it'll bend a little bit in comparison to what direction it's going. And then if we just kind of follow this path along here, we'd have the red light at the very end. And then from right to left, we'd have the Roy BG colors: red, orange, yellow, blue, green, indigo, violet. And that would be my continuous spectra. So again, two ways you can do it. You can either take the white light and you can put it through a glass prism, or you can put it through diffraction grating. It's just going to be different in terms of what happens. So in this case, if you do shine it through the glass prism, it's the violet light that does refract the most. But if you did shine it through a diffraction grating, then the reverse would happen. You'd actually have the red light that is going to bend the furthest from the central antinode. So that's the continuous spectra. And again, nothing new. We've kind of already talked about it. The only thing different here is we talk about how we can actually produce white light. Second spectra is the emission or the bright line spectra. In this, what we're going to do is we're going to take a gas and we're going to heat this gas up. So I'll just take an example of, I don't know, I'll just try to like shade in like a different color of a gas here. So we have this tube, and this tube contains a bunch of this gas. And what we're going to do is we're going to put an electrical current through it. So I'm not sure like what the actual anode and cathode is here. Maybe this is the positive terminal. This is the negative terminal. So we connect it to a battery, and we're basically going to send an electrical current across this tube that contains a gas. Maybe to give an example of this, like some signs on like buildings that you might see, I'm more so thinking of like Las Vegas or just somewhere downtown. They have a neon gas that's contained in a tube. And if you put an electrical current through the neon gas, I believe it starts to glow pink. Or I don't know if street lamps have this in it anymore, but I believe street lamps previously used to have sodium gas in it. And then when you put an electrical current through the sodium gas in the street lamp, then at nighttime it glows that orange type color. So that's how we get it going. If you take a low pressure gas and you seal it inside a tube with an anode and a cathode, it will become hot or excited. So for the time being, we're just going to describe a gas as excited as being hot, although I'm not going to say change the way we think about it. We're going to define what it means for a gas to be excited a little bit later on in the next lesson. So it becomes hot or excited, and then it glows when electricity passes through it. Some of these gases could actually be completely colorless if you just have it in the tube, and then when you do put electricity through it, you can actually see like a different color. What we're then going to do is we're going to take that gas and we're going to direct it through that same prism. So we're going to take this gas and then it's going to approach this prism. So it's a little bit different here. I've taken a gas, low pressure gas, and I'm putting electricity through it. Now, what we notice is that if you do this and you send it through a glass prism or diffraction grating, what you're going to find is instead of having the continuous spectrum of colors from like red to orange to yellow to green to blue to indigo to the violet, all you're going to see is you're going to notice a black background. And on that black background, you're just going to see some very distinct lines. So maybe, for example, you might see a line that's just one yellow line and another yellow line. So this, for example, could be sodium gas. So the sodium gas, if you put electrical current through it, again, it gives you that orange street lamp color. But if you took that street lamp color and you put it through a diffraction grating or a prism, you could actually form a couple of very distinct lines on a dark background. And that's why we call it the bright line spectrum, because we're forming very distinct bright lines. And yes, when you do this, you take a gas, you excite it by putting an electrical current through it, and you take that gas and you direct it through either a diffraction grating or a prism, then you're going to get some bright colored lines on a black background. Should point out though that depending on the type of gas that you use, you're going to get a different bright line spectra. So here's a few examples. So I showed sodium on the previous slides. I believe sodium, if you excite sodium gas to direct it through a prism, you just get a couple of like very distinct red lines. I mean, neon has like tons of them that are in the yellow, orange, red part of the visible light spectra. Mercury, we've got some violet, some blue, some green, some yellow, et cetera, et cetera. So depending on the type of gas used, you're going to get a different number of bright lines and different colors. And again, this was something that physicists could not explain in the classical era. Like, why do different gases give you these different bright lines on a black background? Final spectrum we have is the absorption or the dark line spectra. Okay, so in this case, this is a very similar setup to the continuous spectra. So just as a quick recall, for the continuous spectra, what we were doing is we were taking white light, and then we were just basically taking the white light, shining it through a prism, and it gave us the continuous spectrum of colors. What we're going to do this time around is between where you have the white light and the prism, we're going to put in a cool gas. So this cool gas could be, let's do that sodium gas again. So that sodium gas with like that orange type color, although I think if it's cool, maybe it's not actually giving off color at this point. But anyways, I'll just say that it's a sodium gas. I think it's only when it's excited it actually appears to be the orange color. Okay, so we shine white light through a cool gas. Now, this time what we notice is that we get a continuous spectrum of colors. So over here, we would actually get the Roy G. Biv color. So again, I think red would be here, and then we'd have like orange, yellow, green, blue, violet. So we get a continuous spectrum of colors, but there's some dark lines that are missing. It's like they've been stolen away. So that sodium gas has something to do that. So without the sodium gas, you get the continuous spectra. But if you put the sodium gas there, it actually seems to absorb some of these lines. So what you see is these dark lines of light that appear to be missing. So let's go through this. When you take white light and you pass it through a cool or an unexcited gas, unexcited just means I don't have an electrical current through it before dispersing or diffracting. That unexcited gas in the container absorbs a few discrete wavelengths or colors of light. So it's stealing some of the bands. Now, do you have any idea as to like which specific colors the sodium might steal away? It has something to do with the bright line spectra. Okay, we'll talk about it on the next slide here. So what you end up getting is you get the continuous spectrum of color from red to orange to yellow, green to blue to violet, except you're missing some colors. You have some darker lines. This is a bit harder to see. I mean, the absorption spectra on this picture, I can really only see one dark line. I'm not sure what the gas is for this one specifically, but your one dark line, it looks like it's about right here. So again, your absorption spectrum is you have the continuous spectra of light, except the gas has absorbed a certain wavelength or a certain color of light. And then what you get is you get the dark line on the continuous spectra background. And that's why we call it the dark line spectra, because the gas is absorbing something. It turns out that the frequency of light that's absorbed, so again, let's go back here, because my question to you was, well, which colors are absorbed by the sodium? So the frequency or wavelength the color is absorbed by the unexcited gas exactly matches the frequency of the light emitted by the gas. So this is what this means. So I talked about the emission spectra for sodium. So you take sodium gas and you excite it, put an electrical current through it, you get two bright lines on a dark background. That's called my bright line or my emission spectra. It turns out if you take that same sodium gas and with it cool now, and if you shine white light through it, you get the continuous spectra, but the gas has stolen those two yellow lines. So there's something about sodium specifically that does like these two wavelengths of light. And we're not going to explain it just quite yet. We'll do that once we get into the next lesson and start to modify our model of the atom. But there is a perfect match here. To finish the lesson off, we're going to talk about another scientist, Johann, let me say Jakob Balmer. Now, he didn't do anything to explain why you do get these different lines, but he did come up with a mathematical formula that predicts which wavelengths you're going to get when you take hydrogen and excite it. So the four emission lines in hydrogen we can see. Assuming I was actually like a brilliant scientist, which I'm clearly not, like this is probably the best I could do. Like I could look at an observation and be like, oh yeah, I can come up with a mathematical model for it, but this mathematical model doesn't actually explain why any of this is happening. So just like Max Planck, who kind of like looked at the answer and just changed the wave model to make it work, Balmer here is just going to come up with a model just to match again the answer. So those are my kind of scientists, because again, I would never possess like the critical thinking skills to provide any decent explanation to this stuff. Okay, enough about me though. All right, so my equation is 1 over lambda is equal to RH multiplied by 1 over 2 squared minus 1 over n squared. In this equation, RH is referred to as Rydberg's constant. And again, this is only going to be valid for hydrogen. And for hydrogen, it has a value of 1.097 times 10 to the 7 inverse meters. And to get the 4 wavelengths of, I believe it's visible light for hydrogen, for the value of n, you just plug in the numbers 3, 4, 5, 6. And again, right now, n doesn't mean anything. It's just a number you plug into an equation that gives you the four visible bands of hydrogen when you take hydrogen and gas and you do excite it. You might be wondering, why don't you just write down 1 over 4 instead of 1 over 2 squared? Well, we'll come back to the equation a little bit later once we do modify or model the atom. We'll talk about why we do put it in that format. Just want to point out, you also might be wondering, why don't you start at like n equals 1? If you started at n equals 1, you'd have like a quarter minus 1, which would give you a negative wavelength. Doesn't make any sense. If you started at n equals 2, then you get 0, so that wouldn't work out. Therefore, you do need to start the n values at 3. And if you plug in n equals 3, 4, 5, and 6, you can get the first 4 wavelengths of, again, visible light, I believe. That's going to be produced in the bright line spectra for hydrogen. Yeah, so n equals 3 gives you the red light, n equals 4 gives you the green, n equals 5 gives you blue, n equals 6 gives you violet. If you start to plug in bigger numbers, I think you start to then get into the ultraviolet portion of the spectrum. All right, that's it for this lesson. The assignment for today is actually going to be the second part of the one from the last lesson on the Compton effect. So again, the first part of the assignment dealt just with X-ray calculations. Now this part's actually going to deal with the Compton effect. And if you do want to see an example problem that shows how both conservation of energy and conservation of momentum is used to solve these problems, then check out the content section on D2L. I do have the solution to an example posted now. Although I will say, like, when given a choice, always use conservation of energy. Way easier to use scalars than it is to vectors. And in the next lesson, we're going to talk about the Frank-Hertz experiment, where we're going to do a significant adjustment to our model of the atom. And I'll talk to you then.